remember seminar today, Dan Grayson will speak about algebraic K-theory via binary complexes.
Hello. Let me say I'm delighted to be again a member at the Institute after not being around here much since I was a member previously, 31 years ago. It's just lovely. So the work I'm going to talk about was published in the Journal of the AMS in 2012 in June. So you can read all about it there or on my webpage. The idea that we present is a way to describe Quillen's higher algebraic K groups without homotopy theory. So the main ingredients we'll be using are Grothendieck's definition of the Grothendieck group K0 of M. So here M is some category with a suitable notion of short exact sequences. And Quillen defines something he calls an exact category, which serves this purpose. And we'll be getting to the precise definition later on. But for now, you might as well just think of the category M sub R, where R is a ring, of finitely generated left R modules. And realizing that if R is not Noetherian, then this category might not even be abelian. That has all of the properties and none of the properties you might not think that the most general notion has. And then Quillen introduced the higher algebraic K groups as homotopy groups of a topological space where Q of M is a certain category constructed from M, and we'll get to that later on. And B of a category denotes the geometric realization which one could say briefly is a way of making a topological space out of a category. You put down a point for each object. You put down a 1 simplex for each arrow. You put down a 2 simplex for each commutative triangle of arrows, and so on. So I want to give sort of a heuristic way of getting at the answer that comes out of this work by just starting from first principles and looking at the definition of the Grothendieck group and comparing it to what happens in homotopy theory and in homological algebra to see how one might proceed. So here's the approach that may or may not be helpful to you. Suppose you consider homology groups of some chain complex of abelian group C. Then if you have a class in there of some cycle, then it'll turn out to be 0 if you can write Z as a boundary of something from higher dimension, let's say W. So let's call that a proof that the thing is 0. And examine what happens if you have 2 proofs. If you have 2 proofs, then you also have Z written as D of W prime. And what you can do with 2 proofs is to subtract the corresponding chains in dimension n plus 1 and get a cycle. D of it is equal to 0. And so you get a class in Hn plus 1. So the motto is that 2 proofs of vanishing at level n give an element or class at level n plus 1. This also works with homotopy groups. So suppose X is a topological space and you have a class in homotopy group. So let's let Z be a class like that. So then Z would be a function from the sphere to the space that sends the base point to the base point. And its class in the homotopy group is a homotopy class of that. And if you, you might know that that's 0. And the reason you might know it's 0 is that you might know that Z extends in a certain way to the ball in dimension n+1. So maybe there's a map, let's call it W. And maybe when you restrict to the boundary, you get Z. And then if you have two proofs, then that would amount to having another map. Let's put it up here. W prime, also extending Z. And if you have both of them, then you can patch W and W prime along the common boundary and parlay that into a map from the n+1 dimensional sphere into X, which is composed both of W and W prime. And then you can take the class of that and that'll be something in pi n+1 of your space. So the motto is, two proofs of vanishing in level n lead to a class in level n+1, dimension n+1. So suppose we try that with the Grothendieck group. And just see what comes out. So the Grothendieck group of M, by definition, it's given as by generators and relations. So it's a cokernel of a homomorphism of free groups. Let's take free abelian group on the objects of M. And let's take the free abelian group on the short exact sequences of M. And then this, by definition, is the cokernel of that map over here. And once you write this down, you might think, oh, let's just go further in this direction. We'll have some homological chain complex or something like that. But that doesn't work, because K groups don't come from homology groups of some chain complex. But what does work, we can just follow our nose. So let's suppose we have, so I'm writing angle brackets to indicate a generator of the free group, and then the corresponding equivalence class I'll write square brackets for. And so a typical element of the Grothendieck group would be a difference of two such things, because direct sum helps you combine terms of the same sign into one term. So that would come from the difference of two generators here. And then if you have two proofs that this is equal to 0, well, if you have one proof, that amounts to having something here which hits this difference. So something here well, it's going to have, well, let's just call it W for the time being. And then let's suppose we have two proofs. So we'll have W and W prime. These are elements of this free group. So W minus W prime will go to 0. And let's call that V. And then let's write out what that says. What that says is, well, this is a formal sum over exact sequences with integer coefficients, and some of those coefficients are positive and some are negative. And so we segregate the positive ones from the negative ones, and we put them on the opposite sides of the equation, and what we get is something that looks like this. It'll be a sum. Well, what happened to this map? I should have told you what delta does. So if this exact sequence is called E, then delta E is equal to M minus M prime minus M double prime. So what we find is that we have a bunch of exact sequences over there. Let's index them by I. And these are the ones with the positive coefficients, let's say. And then the ones with negative coefficients will collect together in this sum, indexed by j. Let's call it nj minus nj prime minus nj double prime. And then that's equal to 0. So now let's collect positive and negative terms and put them on opposite sides of the equations. And this is an identity in the free group on the object. So if we write down the corresponding direct sum, the two direct sums on both sides. Oops. Then from the equation in the free group, we know that the collection of objects on the left side is identical to the collection of objects on the right side. So some permutation matrix gives you an isomorphism of these two objects in the category. So let's abbreviate these various things. Let's just call this M and call this N prime and so on. And then what we have is M plus N prime plus N double prime is isomorphic to N plus M prime plus M double prime. And because those direct sums I just took are compatible with short exact sequences, all of these short exact sequences that we had before give direct sum exact sequences, which I can record here. So the subscripts are gone now, and now we can massage that slightly. And so here's the way I want to do it. So those are isomorphic, and there's sort of an obvious way to embed M prime plus N prime as a subobject of this guy. What you do is you embed the M prime into M using this inclusion here. And there's supposed to be a prime here. And you embed the N prime onto that factor, which is equal to n prime. So you do that, and then what's the quotient? Well, look at the part involving m prime and m. The quotient is m double prime. And then this n prime kills that n prime, and what's left over is n double prime. So there's a short exact sequence of our category. And now let's do the same thing down below. M prime, oh, let's do it the other way around though. This n contains n prime. So let's take n prime plus m prime and embed that exactly the same way. The n, except with m and n interchanged. N prime goes into n with co-kernel n double prime. And m prime goes onto that m prime factor, leaving a leftover m double prime. And there are permutation matrices that give isomorphisms of these two. So now, if we call this x, and call this y, and call this z, then we get two exact sequences with the same three objects. One exact sequence comes by going this way, and the other exact sequence comes by going to the top and using that. And the two exact sequences are unrelated. This is not commutative, this square. This is not commutative, this square. These were just accidental isomorphisms of the three objects involved in two short exact sequences. The squares don't commute. So with this definition, we now reduce the two objects to one. They're isomorphic after all, but we have two short exact sequences. And they're both exact, but they're unrelated to each other. So think of this as the top one and that as the bottom one. And this is called a double exact sequence. And when we lengthen it to longer chain complexes, I like to call it an acyclic binary complex. So now I want to show you how when you have such a thing, let's label these maps, I and J and P and Q. No, I want to label them I and I prime and P and P prime. So such a thing should give a class in K1. Remember what stupid philosophy I'm espousing. Two proofs that something vanishes in degree n should give a class in degree n plus 1. So I started with two proofs in degree 0, Grothendieck group, and I should be able to combine them to get something in K1. So I'm going to show you how to do that. So to do that, I have to recall Quillen's definition of the algebraic K group. Oh yeah, let's just bring down that board and write it on that same board. So this category. So QM is a category. And the objects of QM are the objects of M. This is Quillen's definition from his paper, Higher Algebraic K-Theory 1. But the arrows of QM are different. So an arrow, well, the objects are the same, so we can use the same names, let's say, M and N. The arrows are different, so we should draw them differently, so I'll use a double arrow. an arrow from M to N is, by definition, an isomorphism of M with a subquotient object of N. So what does that mean? Well, our category comes equipped with these things called short exact sequences. So every once in a while, you'll have an object that appears in the middle of a short exact sequence, and you'll call the thing to the left a subobject, and the thing to the right a quotient object. And a subquotient object can be viewed dually, either as a subobject of a quotient object or a quotient object of a subobject. And then, how would you picture such a thing? Well, if you think of N as containing a pair of submodules, subobjects, N1 and N0, then you might form the quotient N1 mod N0, and its 0 would be N0 mod N0, and then we would have an isomorphism, let's say, of M with this. So that would be isomorphic like that. And so the picture I like to draw for that is to think of N as a tall line and M as a short line, and think of N0 and N1 as specifying where M goes in like that. And you can think of this as a subobject of a quotient object. The quotient object would be N mod N0, and the subobject would be N1 mod N0. Or you can think of a quotient object of a subobject as it's written here. Either way works. And then you can see about composition of arrows in this category. Well, it's just an obvious thing. And at least it becomes obvious once you write it down. You have a pair of arrows and you want to compose them. So you just do that. And what just doing that means is that you have a pair of subobjects, one containing the other in here. And subobjects of a subquotient object are in one-to-one correspondence with objects in between N1 and N0 in the original guy. And so that gives you the pair that you want in the original guy. So that's how composition works. And then there's some arrows lying around that we can use. So for example, if there are two ways to think of 0 as a subquotient object of any object M. One way is that it's a subobject. So 0 is, think of the pair of objects as being 0 and 0. So 0 is isomorphic to 0 mod 0. And so we'll name this J sub M. J is supposed to imply that that's sort of injective. And then the other way to think of 0 as a subquotient is as a quotient object of M. Think of it as M mod M. And we get an arrow from 0 to this. And so we could call that, I'm going to call that QM. So remember, this is going to be Quillen's definition. So in particular, he's going to be defining or redefining K0 as pi 1. And the isomorphism, which is set up here, is the one that sends a generator M to the path given by these. It's Jm minus Qm. This is a path from the base point to the base point when you take the geometric realization, because in the geometric realization, the objects are replaced by physical points, and the arrows are replaced by line segments, and so on. So that's how that isomorphism is set up, and we want to go level 1 higher and get a map from the two-sphere from something like these two short exact sequences. So suppose we have one of these short exact sequences, then we get some new ways of, in addition to the start with y. There are the two arrows that I just mentioned here that we could use for y, but because y has two sub-objects equal to x, we can do something new. So let's take one of them. If we think of x as a sub-object using I, then that gives an arrow in Q. If we think of 0 as a sub-object of x using the inclusion, then compose that, then that ends up giving 0 as a sub-object in y, which is the same as j sub y. And alternatively, we can think of 0 as a quotient object of y, and think of z as a quotient object of y using p. And if we think of 0 as a quotient object of z, and compose these two arrows, we get q sub y. But the really interesting case is what happens when we do the other thing and think of 0 as a sub-object of z. Oops, the subscript here is wrong. Think of 0 as a sub-object of g, and then here z is a quotient object of y. Well, then when we compose, we're going to get the sub-quotient object of y that corresponds first modding out by z and taking the 0 sub-object in that. So that'll essentially be z mod z as a sub-quotient. No, x mod x, the kernel. Similarly here, if we take 0 as a sub-object of, as a quotient object of x, take 0 as a quotient object of x and x as a sub-object of y, then again, we'll start with x and take its quotient by itself. That's x mod x. So these two triangles show that this square commutes. So here we have commutative triangles, 4 of them, in the category QM. And think of taking a 2-simplex and subdividing it this way, and you'll get a continuous map to the geometric realization of QM by following the prescription there. And then look at the boundary and see that the boundary doesn't involve I and P at all. It just involves the 3 objects. And the canonical maps J and Q. It doesn't involve I and P. So remember, we have 2 of these things. We have IP and we also have I prime and P prime. So we have 2 ways of mapping this thing in with agreement on boundary. And so by gluing, we can parlay that into a map from S2 into BQM and take its homotopy class, and that gives us something in pi 2 of BQM, which is K1. This is the most technical part of the talk, I promise. Are there any questions about it? About what the geometric realization is? Are you doing geometric realization at 4? Anyone who wants to find out more about geometric realization should come to this room at 4 o'clock, and Mike Schulman will explain it. All right, so that's the motivation. Oh, and I think it's worthwhile pointing out what the boundary is. The boundary is composed of 3 paths of this form, which I advertised were the paths that in K0 give you the class corresponding to the object. So if you follow the loop specified by the boundary here, you'll be following a loop in pi 1 of this space that corresponds to the class of y minus x minus z. And then we have 2 ways of filling this in from a map from the 2-ball to the space, 2 proofs that it's 0. And so it's, in other words, we're proving twice the equation that y is equal to x plus z, which is what short exact sequences do in the Grothendieck group by definition. We're proving that twice and using that to get an actual map from the two-sphere in. So now I can mention what Alexander Danashef did with this idea. He got very energetic and wrote an inspirational paper where he showed that those things generate K1, and he gave explicit relations. So that you get a presentation of K1 that works for any exact category. So how do you go further? Well, going further requires lengthening the short exact sequences into longer chain complexes. So use longer chain complexes. So for example, you might have, well, they would still be bounded. You might have a sequence of objects, and you might have two ways of putting differentials on it, unrelated to each other. So that both ways are acyclic. Both top and bottom are acyclic. And then these also give classes in K1. So as an exercise to see whether you understood this thing, you can try to just extend the thing that we did here to those guys. So why do we have to lengthen it? Let me just say the reason. The reason is that even if you start with chain complexes of length 2, then you very quickly led to chain complexes of length 3 because you want to take mapping cones. You might have a map between two chain complexes, and then you might want to take the mapping cone, which is gotten by adding up like this. So you get M2 going to M1 plus N2, going to M0 plus N1, going to N0, and now suddenly you have a chain complex of length 3. The mapping cone turns out to be important. Once you have the mapping cone, you get to use standard machinery of homological algebra. So now let's get into saying what kind of category. Oh yeah, this is dispensed. What kind of category we use. The notion of exact category due to Quillen isn't immediately amenable to homological algebra with longer chain complexes because by definition it just consists of these things called short exact sequences. So, oh, that reminds me, I should turn my phone off. Oh, it is off. So here's the type we consider. So we consider good categories M that have an embedding, a full and faithful embedding into some abelian category with two properties. Property one is that if you have a sequence 0 to M1 to A to M2 to 0, which is exact in A, and these objects are in the subcategory, then A is isomorphic to an object of M. Oh, you can't see that, sorry. It says A is isomorphic to an object of M. And then the second property is that if you have a sequence of objects bounded of this subcategory, which form a long exact sequence in A, I should also have said here that this sequence is also exact in M. Now this should be an exact functor, and this sequence should be exact also in M. And then here, if you have a long exact sequence in A whose objects are in M, what we ask is that the images of the differentials should all be in this isomorphic to objects in the subcategory. So the reason for that is that then you can think of the long exact sequence as being gotten by splicing together short exact sequences. And the short exact sequences are specified by the data, an additive category together with a family of short exact sequences. So then the notion of long exact sequence is something that can be defined in terms of the data you have at hand. And then with this property in hand, the long exact sequences behave well in the ambient abelian category. And so all of the standard facts about long exact sequences suddenly become true, and you can use homological algebra. So for example, if you have a short exact sequence of chain complexes and any two of them are acyclic, then so is a third. This is something you couldn't prove without some other condition on the exact category. So I should mention that the category M sub r that I mentioned before has that property. And projective finitely generated left R modules have that category has the property, but the category of free finitely generated left R modules does not necessarily have that property, because you could have a stably free, non-free R module, and you could put it in the middle of an acyclic chain complex of free modules of length 3, and it would contradict this this assumption we're making. So, but it's actually a very mild assumption, because that sort of thing that's involved with the stably free, non-free modules is the only obstruction having this property. And in any case, all of the categories you run into have the property. And in any case, you can relate. You can always coerce a category into having this property without doing too much damage to the K-theory. So what's the theorem that comes out of it? We take the following notation. So CM.
I have a question about two.
Yep.
Are you saying that any such long exact sequences is spliced together from short exact sequences in M?
Yeah, yeah. So, oh yeah, I should have said that. All the images, well, yeah, once they're in M, then they're, here, let me just draw a picture of how that works. So let's take one of length 3. And let's suppose that the image here, let's call it B1. So that sits inside M1 and is a quotient of M2. And if that's in the category, then we can forget about the long exact sequence and just remember the 2 short exact sequences. And we can recover the long one from the short one by remembering the identity map there. Did that answer your question?
Yeah, I just wanted to visualize it well.
So CM will denote the category of bounded chain complexes in M. And BM will denote the category of bounded binary chain complexes in M. So I've already said what binary means, but let me repeat it. It means it has 2 differentials, unrelated to each other. And then we introduce CQM for the acyclic ones. In CM.
What are the morphisms if you use it?
Oh yeah, what are the morphisms? Well, so a morphism is first of all a morphism of underlying graded objects. And there are 2 commutativity statements. The square with the upper differentials commutes and the square with the lower differentials commutes. And then BQ of M is the acyclic ones in B, by which I mean acyclic on top and bottom independently. They're unrelated differentials, so acyclicity of one doesn't imply acyclicity of the other. Q here stands for quasi-isomorphism. And then we take, there's one, remember my basic philosophy that I espoused, which was that if you have 2 proofs in dimension n, you get a class in dimension n plus 1. Well, if those proofs were the same proof, you should get the 0 class in dimension n plus 1. So the way we get rid of the trivial proofs where they're both the same is by constructing them in the following way. There's a functor from CQ to BQ, sort of a diagonal functor, let's call it delta, which takes a graded object together with a differential and sends it to the graded object with 2 differentials where they're both the same as what you had before. Those correspond to the trivial ones. So this is an embedding, and there are 2 projections back down to CQ by forgetting the bottom and forgetting just remembering the top differential, or alternatively just remembering the bottom differential. And then in algebraic K-theory, there's a way of thinking of delta as a pair of exact categories. And there's a very formal way of extending the definition of higher algebraic K-theory to pairs. So we give a name to the pair. We call it omega QM. And then the theorem is you take the K-theory of that pair. Oh, wait, I think I'd prefer not to write the Q. It should be implicit. If you take the K-theory of that gadget as a topological space, using Quillen's definition augmented as I just said, then this is homotopy equivalent to the loop space of the K-theory of M. Now I'm going to put parentheses here with K naught of M discarded. So there's a way in topology when you have a topological space to discard the bottom homotopy group. For example, if you have a disconnected space, you can just take the component, the connected component of the base point. So you discard K naught, take the loop space, and this is what you get. So corollary of the theorem is that K0 of this gadget is K1 of M. Because what loop space does is it shifts things over. Pi n of the loop space is pi n plus 1 of the original space. And the thing can be iterated. So let's let n be a natural number and then just repeat. So this omega m I'm advertising as a pair of exact categories, and I'm advertising the philosophy that a pair is just as good as having one. And it's something we can apply the whole previous construction to. So we can take omega of m, and we can repeat that n times. And let's call the result omega to the n of m. And so repeating it, this thing is homotopy equivalent to the nth loop space of the K-theory of M with n homotopy groups removed. And so a corollary of that is that K0 of omega n of M is isomorphic to Kn of M. And so that gives explicit generators and relations for Kn of M. So let me just spell it out, what that means.
May I
Yeah.
ask a question? I'm a bit confused by your theory because K of exact category was a graded commutative group, if I understand well. So
Oh,
why
yeah.
do you say that it's
Well, oh yeah, so this, my notation now is the space. So I didn't write a subscript here, and I should have explained earlier, thank you for the question, that K of M is defined to be the loop space of BQM. It's this topological space. So it's the space whose homotopy groups are the K groups. So pi n, so Kn of M is pi n of the space Km. That's how the indexing works. So I'm talking about the space. So the deal is that this omega construction, it's some sort of loop space construction on the level of exact categories that mirrors the loop space construction on the level of spaces after applying the K-theory functor from categories to spaces.
so when you write
That's exactly right. So, yeah, so in other words, here's the definition that I apply here. Yeah, so, I mean, for example, well, you might have further questions. But let me just spell out what this means explicitly. So, it means Kn of m is generated by n-dimensional, let's put it this way, by z to the n graded, bounded, graded objects of m equipped with two differentials in each of the n directions. So let's call them di and di prime. And then remembering the answer to this question about what the morphisms are, one sees that the differentials have to commute with each other to a certain extent. Di commutes with dj for I not equal to j, and di also commutes with dj prime, and di prime also commutes with dj, and di prime also commutes with dj prime. But there's no relationship or commutativity between differentials that go in the same direction. They have to obey this sort of commutativity because that each dimension was added onto the previous one using this same construction where this is the definition of a morphism in the category. And then the relations are of two types. There's the one coming from short exact sequences, just as in the definition of Grothendieck group, you could have a short exact sequence of such things. And then the second relation is that if there exists an I so that the two differentials in the ith direction are equal, then you have to get 0. And that is a consequence of what I said about having to get rid of the case where you take two proofs that are the identical proof. And those are complete generators and relations for the thing, and that's the answer. These are what I call n-dimensional acyclic binary multi-complexes. So what good is this if
Can you put some bound on the size of these?
yes,
And the length of these things?
yeah, I have a lemma. Length 2 is enough in every direction. So you can reduce everything to a cube of volume 2 to the n. The lemma is, has sort of a complicated proof, so I haven't written it up yet or needed to write it up yet. But it sort of motivates Nianashev's result that the length 2 things generated K1. Even though this, I don't directly recover his result. His result is phrased in such a way I don't see how to recover it exactly. Length 2 is enough. What if you could get to length 1? This is the holy grail. So length 1,
So all these things are acyclic in every direction.
yes. Oh, I thank you. I forgot to say that. Equipped with, yeah, let's insert the word acyclic. It should go right here. Two acyclic, oh, you're on the ball. Congratulations. Two acyclic differentials in each of n directions. What was I about to say?
Length 1.
Oh, yeah, length 1. Yeah, what happens if you're down to length 1 already? Then both differentials give acyclic chain complexes, which mean that both of these maps are isomorphisms. Let's call this one D and this one D prime. So if you take something like D inverse D prime, you get an automorphism of M1. So length 1 means you're down to automorphisms. This corresponds to the class of an invertible matrix in K1. This corresponds to a Steinberg symbol in K2 when you have a square with 2 units. And this corresponds to what happens in motivic cohomology. So the best consequence I have of all of these considerations is a new proof of the construction of the spectral sequence that connects motivic cohomology to algebraic K-theory using these ideas. Although it does not depend on these generators and relations per se, but depends on the space level construction. Motivic cohomology from the point of view of the spectral sequence can be seen as the obstruction to representing elements of K-theory by cubes of size 1 in every direction. And then the second direction I'm extending these results in is to handle the case of relative K-theory. And then with that, one could present the long exact sequences of K-theory without using homotopy theory. This just presents the groups, not the long exact sequences. But it seems to be really hard to reprove with this as a definition the basic theorems of Quillen that he proved in 1971. So even if someone had thought of this in 1971, probably it wouldn't have survived as the definition in those days because the basic theorems just are not accessible. So the only one that I've managed to prove is the resolution theorem, which says that modules of finite projected dimension give the same K-theory as projective modules. But the other ones, like localization for abelian categories and dévisage, seem to be inaccessible at the moment from this point of view. Even proving the Steinberg relation, u comma 1 minus u in K2 seems to be inaccessible. Although I've made, I've gone halfway. I can take a proof from motivic cohomology and take the diagram, the multi-complex that represents u comma 1 minus u, and parlay it from a 1 by 1 diagram into a 2 by 2 diagram where u and 1 minus u no longer have to be units. Now they can vary. And so that ought to eventually lead to an actual proof in this framework, but perhaps it's not so urgent. Still, that would be a great exercise for someone who wants to do something that seems hard to do. So thank you for your attention.
Thank you very much.